Okay, I've started recording now that we've missed the first half. Should I upload it? There's going to be no audio, but someone could follow along with the tinkering I've done if they find it helpful. Should I upload it?
Why not?
All right, I'll just add a no audio.
It might be nice for like you're like, wait, how do I adjust the weights again? Like if I was here in the lecture to go check that.
Okay, yeah, and I'll just add a warning. So I'll be looking for your comments. There's no audio. Like, thanks, a-hole. I know. All right. Anyways, okay, yeah. I lost my train of thought. There was if I was doing it and I noticed, look, the fourth column, that fourth independent variable ain't popping up. And I'm getting the sense, and I want to be clear, I generated these a long time ago. I don't remember what I did, okay? I don't even think I have them saved anywhere. I think I wrote them once, the functions to generate them, and that was that, right? So there they were. The reason I'm asking you to tell me the functions is because I want to remember. If in practice I was doing this and my job was like, what are the relationships here? And I'm finding that one of those independent variables is not related, seemingly unrelated at all, I might just make a copy of the data file and eliminate it in that one copy, just to reduce the search space. I don't want the search space to be any bigger than it needs to be. So I would actively go in and just delete a column in the CSV and just move everything and try again and simplify it. I would do that. Because my conclusion, you remember, like pretend these data was recorded by something, a sensor or a human, they recorded it. They just recorded everything. If you're finding that GP is excluding one of those independent variables, if you haven't noticed, genetic programming will do feature selection automatically. It automatically will ignore them in the trees if it's not helpful. So you got to figure these algorithms don't do the job for you, they augment your job, and you have to work with it. So you do that, and you're like, okay, it's kind of it's selecting out that one thing. Let me go back and assume that that one observation was irrelevant, and let's try again. Because at the end of the day, the goal is what is the relationship in the data? Yeah. But interesting question, yeah. Other questions? This is a very interesting question. Okay, now for a lecture part. Who here started assignment 3? What? You kidding me? You haven't started assignment 3? Oh, right, assignment 2 is not even due yet. Right. Okay, tuning hyperparameters. Ooh. All right, all those evolutionary algorithms, I mean, not even just evolutionary algorithms, there's going to be hyperparameters that you need to tune. And given the modular nature, this is something you have to really think about too, is given the modular nature of these evolutionary algorithms, those like modular bits themselves are like hyperparameters. It's not just, oh, what was my tournament size? It's not just what's my crossover rate, but also what's your crossover, right? That's also something that's tunable. And some of those come with their own new hyperparameters. Like if you do roulette wheel selection, you're doing roulette wheel selection. If you're doing tournament selection, well, now you also need to specify tournament size. So symbolic versus numeric hyperparameters. Your symbolic hyperparameters are your things like those modular things. What was your selection strategy? What was your crossover? The numeric ones are, well, what's your crossover rate? What's your mutation rate? How many generations? What's the tournament size? Which, of course, is dependent on the fact that you picked tournament selection. Regardless of the hyperparameter type, a value needs to be picked. A crossover rate needs to be set. A decision needs to be made on what the selection you're going to use is, and depending on that, yeah, you might have more hyperparameters to pick. One of the big criticisms of evolutionary computation is the number of tunable hyperparameters you have. It ends up taking a lot of work to get all those settings right. Now, fortunately, in order to get good results, that's kind of a bit of a, They're not, people making that point, they're not wrong, but fortunately, you've probably discovered by now, even without spending a crazy amount of time tuning your crossover rate, you're still going to get good results, right? When you were doing your TSP assignment, you pick a crossover rate of like 80 and we're like, okay, that's good enough, right? You didn't tune it to like, oh, it's like 83.7141222. That's a really good one. Well, no, you just pick something good and you go with it. So it's not that important. If you're really trying to squeeze out every last little bit of oomph out of your algorithm, maybe you go crazy tuning those parameters. But it's not, you don't have to go that crazy. Typically, your symbolic hyperparameters are more high level. They are like what make up the evolutionary algorithm. A lot of times, the evolutionary algorithm framework is just the framework. Your symbolic hyperparameters, if you pick the right ones, you've got genetic programming. You've got differential evolution. They are like what makes up the algorithm. And the numeric ones, they're the low-level ones. And then, if you want to use some terminology that the textbook uses is, once you've set all your hyperparameters, you have an evolutionary computation algorithm instance. Fine. Tuning hyperparameters. Well, I got bad news. There's no good way to go about doing it other than you just do it. Usually what I do is you start with reasonable starting values, crossover rate of 20, no, a crossover of 80, a mutation of 20, population of maybe 1,000, start with 10,000 generations. Yeah, that's probably a good starting point. And just play from there. You don't have to get crazy, right? Like, there we go. Now, depending on the algorithm you're using, like, okay, if I'm using genetic programming, 20% mutation would be considered very high. And usually with genetic programming, you have larger populations, right? So maybe a population of 100 is too low, right? Fine, right? There's choices there. But you could start with some very simple, reasonable starting places. Some of these hyperparameters, though, are kind of difficult to have like a good starting thing on, like population size. It's reasonable to increase the population size if the results improve as it grows, but depending on the selection strategy, it might also maybe require you to adjust the tournament size. So the story so far this semester has been like, a lot of these values are so inextricably interconnected and not independent. They're so dependent on one another that if you change one, you kind of have to change the other. And that's, we all kind of know that. That's kind of the game we're playing here, but just be aware of that. And then once you've got your starting place, you do some empirical tinkering. All I mean is you set some values, you hit run, you're like, okay. You change the value, you hit run, it got better. Ooh, good, right? That's what I mean. You just kind of play around a little bit. And this takes a while. Who here probably thinks, yeah, I spent a lot of time doing this on assignment 1? Really? No? Oh. Usually that's what takes a while. It's just kind of playing around and being like, okay, that was good, and maybe you changed that, and maybe you should have. And sometimes you'll see like, okay, maybe as I change one parameter value, it really affects the algorithm's performance. And maybe as I change mutation rate, it really didn't actually have that much of a difference. It's possible that some values that you change have no real meaningful impact, but this is going to be problem dependent and instance dependent. Maybe TSP, it's better to have a low mutation rate, right? But on one particular instance, maybe a little bit better is better. I don't know, whatever. It's all hard to really say. There's no one answer to any of this stuff. And this right here, just kind of showing that same thing, but like it changes between problems. On some problems, some values for a hyperparameter will be good on some problems, but really bad on other problems. And on some problems, changing a hyperparameter will have a big impact or very little impact. It's hard to say. All of this so far is to just say, good luck. Start with some values. tinker a little bit with change this, see what you get, change that, see what you get. If you get better results, good. If not, whatever. That's the game we play. Don't ever sit down and say, okay, I'm looking for the best hyperparameter configuration. That's a foolish thing to do. You're never going to find it. It would take you forever. It's a pipe dream. There's literally an uncountable infinite number of configurations, right? You've got you've got floating point numbers, right? It's not going to happen. Don't do it. The trick is to run your algorithm repeatedly and tune the hyperparameters until you get adequate results that you're happy with. With experience, this process gets a little easier. You gain some intuition, but there's really not too much intuition to be gained. Just trust your gut. Now, do know that if you go looking, there are automated processes for tuning hyperparameters. There's like grid searches. You can go probably find like pip install something, 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 and it'll do it for you. They're not great. They really probably aren't going to outperform you by just tinkering. It might be able to squeeze out a little bit of extra performance, maybe, but I don't know. I've never found them to be worth the pain. I could be wrong. If you want to try them, go for it, by all means. But the whole point of this is we got to pick some hyperparameter values, and I want to find good ones. After I've spent some tinkering, I want to find some good ones, let's say. And it might be the case that I find multiple sets of configurations that are giving me good results. Or maybe I want to ask the question, I have a new crossover I want to implement. Did changing that hyperparameter, because the crossover you use is a hyperparameter, did changing that improve results, right? Was it actually better? When you worked on assignment 1, bless you, every time you hit run, you got a slightly different result, right? You could come up with a hyperparameter setting, you could hit run, and it might give you a terrible result. But you really shouldn't conclude that that must be bad. You should probably run it a few more times to get a sense of the result it's getting you, just because it's pretty random, right? So if I have a crossover I want to test, I've invented a new crossover function. And I think it's better than all the others. How do I go and show that it's better? Every time I can't just take a GA with crossover A and hit run, get one result and be like, okay, that's the result. Crossover B, hit run, get the result. Crossover C, hit run, get the result. And then my new crossover, hit run and get a result and be like, mine was the best, therefore it's better. I can't do that because we know every time I hit run on each of them, I get a slightly different result, right? And every time I hit run on the other one, I get a slightly different result, a slightly different result, slightly different. I can't just do that. So how do I actually compare instances? What's going on there? That was interesting. Does it do that normally? I've never seen that happen before. That was weird. How do I actually compare? Now, first and foremost, what I'm going to go, raise your hand if you've taken stats. Okay, I'm going to try to teach you what stats didn't teach you. That's not to shit on your stats courses. They are what they are. But I'm going to try to teach you something that you never learned in stats that I really wish you did. And this kind of explains a lot of what you've been doing in your stats class without being taught what you're doing in your stats class. But I'm not going to go into a lot of detail on this. All right? I'm going to keep this high level. I'm going to skip a lot of the formalisms. There's going to be things that I'm going to say that are not very precise, maybe slightly inaccurate. But I'm doing that by design because I want you to get the intuition behind what I'm doing. All right? This high levelness and that impreciseness should be sufficient to give you the ideas that I want you to take away. So consider a random variable. Consider a random variable as some phenomenon that can be observed. Raise your hand if you've heard the phrase random variable before. If you've taken stats, you absolutely have. You've just suppressed that, I understand. So random variable, it's not really a variable, it's not even really random, but it's the word we use to say I'm observing something, and I can measure something about that thing I'm observing. We want to take some quantitative measurement. Maybe it's time to recover from the flu. The amount of nuts a squirrel buries a day, the number of people with blonde hair that walk by this building between 10 and 11 a.m. on Tuesdays, or the best fitness value of a genetic algorithm. There's something I can look at and I can measure. But I mean, if I go outside and I'm observing squirrels burying nuts every day, every squirrel is going to bury a little bit different number of nuts. And maybe one day they bury a few more than another, right? It's never going to be the same. The consistency is really not there. But that's the idea of a random variable. Whatever the measurement is, I can record that measurement and I can save it as a distribution. So consider the following two random variables. I've got some random variable represented by this gray box. Okay? I'm observing it. And as I observe it, the first thing I observe out of it is 15. Then I observe a 19.5, then a 15.8, 15.3, 12.65. I'm just observing it. What I'm actually observing is irrelevant. I've got a random variable, and I'm making this observation about it. Maybe it is average number of nuts the 5 squirrels that in my backyard bury a day. Maybe that's what it is. Maybe it's flu recovery time. Maybe it's the fitness of your algorithm. I don't know. But I'm making these measurements, and then once I've gathered them all, I don't know how many I have. Maybe I record 100 days. I don't know. I can represent it as a distribution. Okay? And this is the distribution. All right? Are you comfortable with what this means, what a distribution means? There's like buckets here. It's the number of things that fall between the range of that and that, you know. Cool. And here's another distribution. All right? Oh, it's 50 data points. There we go. It's actually just 50. So I'm observing this box, and I'm observing that box. One's dark gray, one's light gray. They seem different, and I'm just making measurements and I'm recording the stuff. All right? Is this okay? I want to make sure everyone follows because it's critical that we're following along before we keep going and we get too deep into this. In fact, I'm aware of the time and I don't really want to break this lecture in half. So regardless of what these random variables are, one may wonder, that gray box and that light gray box, you know, they had similar-ish outputs. Are they actually different? So if I'm considering flu recovery time, the random variable may be the recovery time of two different groups of people. Does one group recover faster? Maybe I've got a group of children and a group of adults. Which group recovers faster? I think the younger group will recover faster. All right, measure. Did they? I think people with shoe sizes above 10 recover from the flu faster. Okay, you can do that. The random variable is people with shoe sizes above 10. I measure the recovery times. And then the other one is people with shoe sizes less than 10. Measure the recovery times. Whatever. It doesn't matter. It can be literally anything I want. I'm making a measurements. With the squirrels, Does one squirrel bury more nuts in a day than the other? I think that one squirrel is far better than the other one. I think it's way better at gathering and burying nuts than the other. Okay, test it. You can actually measure and check, is it actually better? Does one year have more blonde people walking past the building on Tuesdays at 10 to 11 a.m. than another year? One of those boxes might be 2020 and another box might be 2023. Does one evolutionary computation algorithm implementation perform better than another? Does your crossover rate actually perform better than another crossover rate? That's what the random variables could be. I'm making some measurement on it, and I want to see what those results are so I have those distributions. So the goal is there a difference or not? We've got the gray boxes distribution, we've got the light gray boxes distribution. If I plot them against each other, we can immediately do the first thing we like to do, which is the eyeball test. Are they different? When I'm comparing these random variables, I cannot compare any one value because there is no one value that that random variable gave me. I've got a series of pieces of information. I've got a lot of data there. I've got a distribution. So what I have to compare, what I have to be focused on, are the distributions. So when I'm saying, are these random variables different, really what I want to know is, are the distributions of the things I'm observing different or not different between these random variables? That's the big question I have. When you do an eyeball test looking at these things, do these distributions look different to you or not? Yeah, a little bit, but you know, but that's the thing. Right now we're in a position where we're like, it looks like it, but you know, this was from 50 observations of each. If I actually had 100 observations of both, what would this look like? If I were to delete this and do another recording, the distributions are going to be a little different every time, because every time I make an observation, I'm going to get a slightly different result. It's never nice and consistent, and sometimes it is, but often it's not. So if I were to, I accidentally got confused about my data, maybe I need to start over, and I generate a new distribution of the top one and the bottom one, the distributions are going to look a little different. So when I compare the distributions, it's going to look a little different. So when I asked, are they the same? And we got like, yeah, maybe, I don't know. That's the question. We don't know. We have to compare these distributions. So what I want to know, here's the big question I'm asking is, and this is often why we start with the null hypothesis. I'm going to start by assuming there is no difference. Assume that those distributions are actually the same. Assume that people with the feet that are bigger than size 10 really don't recover faster than people with the feet smaller than size 10. Right? To be clear, when I'm saying shoe size of 10, I'm making a point that it's a silly, arbitrary metric. Anything I want to compare, I can. When visually analyzing these things, there does appear to be a difference, but the data is clearly noisy. A range of values are obtained for each random variable, and there's only 50 observations of each. So it's difficult to truly say if the random variables are truly producing different distributions. They may effectively be the same. The two groups do not take the same amount of time to recover from the flu. Maybe the squirrel I named Jimbo does not bury more nuts than the squirrel I named Sir Laura. There really isn't more blonde people this year versus last year. Or my algorithm really isn't performing better than the next person's. Maybe that's the case. And that is the null hypothesis. Raise your hand if you've heard the null hypothesis before. Of course you have. The null hypothesis, you start by saying, assume there's no difference. And this is important. It's important to assume there's no difference. Now, you don't need to assume there's no difference to come up with the important logical chain of thinking, but it helps. If we assume there's no difference, this is what we'll end it today. If we assume there's no difference, then it should, We're doing a drug trial. No. I've got my 2 squirrels. If I assume there's no difference, then it should not have mattered if you gave, I'm observing the squirrel. I'm trying to think, what's the best way to explain this? If there's no difference, the value I got, the value of I observed, could have come from either squirrel. The number of nuts I saw them bury that day could have come from either squirrel. If there is no difference, then it shouldn't have mattered what value, or sorry, which random variable that value came from. And if it doesn't matter what value that random variable came from, maybe we could pretend that those observations came from some arbitrary one of those 2 random variables. And if we do that, we can regenerate the distributions and compare the distributions. We'll pick up here Friday.